Good day, Math 30-1s. Today we are continuing the idea of logarithms, but this time with transformations. Last day we learned what a logarithm was. We learned how to sketch it. We learned the loop, the connection between exponents and logs, and how to equate the two together, and a little bit of an application involving earthquakes. As I said, today we're learning transformations, and there is still this idea that we can use mapping notation, but we're going to start off with a simpler case and then eventually work up to something more complex. The parameters that we're dealing with may have different letters, but they are still the same idea. We're comparing this to some logarithmic function with a base, we'll call it c, and some input x. Now when you're looking at the input x, it requires us to still have a factored b value. This represents our horizontal stretch by a factor of 1 over b, our flips as well. It represents our horizontal shift or translation. Now if there is a multiplication in front of the log, this represents our vertical stretch a, or our flip, our reflection. And it also could involve, if there's an addition at the end, a vertical shift, up or down k. So as I said, we're going to look at a simple case which forces us to think about what the logarithmic graph looks like. A shift 3 to the left and 2 up. And after this we'll look at maybe a more complex example that requires mapping notation. So to start, let's try to avoid having to do two charts and think about log base 2 of x in one graph. Now a reminder, we're comparing 2 to the x as an inverse, which means we're flipping the x and y. So I could simply say, let's plug in a -2, -1, 0, 1, 2, 3 into a exponential function. Let's see what comes out. So you can see I'm pretending that the x and y are switched and I'm doing an exponential function, but really we're producing the chart for a logarithmic function. So I'm thinking about 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 2, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And we have a table for log base 2 of x, simply by looking at our y equals 2 to the x exponential function and switching the x and the y. So as we graph an original function, we have to be a little bit careful around our fractions like 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3, and 16, 4. And we can make a nice smooth curve connecting all those dots, remembering that we are approaching an asymptote, which is the y-axis, which we can never quite cross, unless there is a translation or a reflection. So what we're doing is we're taking these points and we are going to move them at the same time 3 left and 2 up. This is a simplified, or maybe just a simple logarithmic function which doesn't require too much thought. So let's take this one dot here in the bottom left, the first one we made, and move it 1, 2, 3 left, 1, 2 up. Many people at this point might feel a little bit stressed and might provide a little bit more structure to their logarithmic graph and draw that vertical dotted line, the asymptote. See, it moves 3 left, just like that first point. So let's continue with moving these points and just say 1, 2, 3 left, 1, 2 up. 1, 2, 3 left, 2 up. 1, 2, 3 left, 1, 2 up. And I missed this one. 1, 2, 3 left, 2 up. And 2 more. 1, 2, 3 left, 2 up. 1, 2, 3, 1, 2. And without too much work, we can produce a logarithmic function if we think that it could be drawn for our base function and then a small enough change. It works. But what if, as we flip it over, we're maybe looking at a vertical flip, a horizontal stretch by a factor of 1/2, a shift 2 units to the left. Remember, we're going to have to factor out that b, and then shifting 1 down. Let's just make sure we don't make a mistake with that b value and rewrite this with that 2 factored out. Now, we are drawing this with 1, 2, 3, 4 different effects, which is maybe complex enough to be a little bit careful. So let's think about the original points that were on our first log base 2 graph, which were at a 1/4, -2, a half, -1, 1, 0, 2, 1, 4, 2, an 8, and a 3. And we're going to map these all over from these x, y values onto some changing x. Well, it's timesing by a 1/2. Remember, it's a reciprocal effect. Timesing by a 1/2 and then 2 left. So timesing by a 1/2 and shifting 2 left. Our y values are being flipped and shifting 1 down. So let's say -y and then subtract a 1. So we have to do this to all these points. So one step at a time, let's maybe do all these x values. If we take this 1/4, times it by a 1/2, and then subtract 2, we end up with a -1.875. If we take the 1/2, times it by a half, and subtract a 2, we have a -1.75. Continuing that trend, it's a -1.5, a -1, a 0, and a 2. For the y values, starting with that -2, if we times it by a -1 and subtract 1, we do end up with a +2 minus 1, or a 1. And again, continuing the trend, -1 times a -1 gives us a 0. And then a -1, -2, -3, and a -4. So these values on the right here are our transformed points on our new transformation. So let's graph these without having to produce the original function. We have a -1.875, which is a bit tricky to be exact with, but let's just say it's very close to -2 and up 1. We have our -1.75 at 0. We have our -1.5 down at -1. At this point you might be thinking, uh-oh, I may have done something wrong. They are still almost, we'll say collinear. It's not linear, but they're still traveling in the same trend, so that's good news. A -1, -2, a 0, -3, and a 2, -4. Well, remember that there's a vertical asymptote on the y-axis that is shifting 2 to the left. Let's draw that dotted line to give us again this structure and say there's our asymptote, and now it makes sense that we're approaching it. There's a vertical flip, which means we are still approaching this asymptote. We're just traveling more slowly to the right and traveling up to reach the asymptote. Now there's a few questions that we might start to think about when considering characteristics. In looking at the visual above and comparing it to other logarithmic functions, what is the domain? Well, for this one, the domain is typically everything to the right of 0. But because there is a translation, we might say for our domain that x is such that x is greater than, not equal to, greater than -2. It is every decimal infraction. It is an element of the real numbers throughout. For the range, all logarithmic functions are an element of the real number system. Our asymptote is tied to that domain and is at y equals -2. And the intercepts, if possible, these might be a little bit tricky. I do see a y and an x-intercept. To find an x-intercept, we would need to say y is 0. To find a y-intercept, we would need to say x equals 0. Let's try this. It might be a little bit tricky, but we'll see what happens. So let's say 0 equals negative log base 2 of 2x plus 4. Can this be evaluated? And there's a subtracting a 1. We're running out of space. For the y-intercept, we are saying x is 0. So can we evaluate y equals negative log base 2 of 2 times 0 plus 4, subtract 1. Okay, well, let's maybe start with the y-intercept 1. That actually piqued my interest for a moment because I saw 2 times a 0, that's a 0 plus a 4. And what we end up with is a negative log base 2 of 4, subtract a 1. If you were asked to evaluate log base 2 of 4 from last day, you might say 2 to the what is 4? And you might say 2 to the 2 is 4. The answer for this expression is 2. So this was chosen very intentionally so that we could say negative 2 subtract 1. Negative 2 minus 1 is negative 3. This should be our y-intercept, which it is. We may not have had to actually do that algebraically, but it nicely confirms it. Well, this one might be a little bit more challenging, but let's try it. What we have is a y value that's 0 and a bit of a mess on the right side. Well, the loop is implicit in this question, but not until we have everything save for the logarithmic part without the a and the k there. Let's add the 1 over to this side and divide both sides by negative 1. We result in a negative 1 that equals a log base 2 of 2x plus 4. We can actually do the loop at this point, which says 2 to the negative 1 is equal to 2x plus 4. And all of a sudden we're solving a linear equation. So we've got a 1 over 2, or 0.5, that equals a 2x plus 4. Now, if we take the moment, and because I'm running out of space, and we're pretty good at solving linear equations, if we take that 0.5, subtract a 4, and divide by 2, we end up with an x value of negative 1.75. And there's your x-intercept, which is confirmed in our negative 1.750 and our 0, negative 3 that we had only moments ago. So this is mapping notation and a little bit of characteristics, which means we might be expected to have to work backwards as well. And in this one, I have determining an equation from a graph example, starting with log base 4 of x as a function sketched. Question is, determine the new equation from some graph that's been transformed. So you might ask yourself, well, what has changed? Could there have been a translation to the left or right? Well, the asymptote hasn't changed, so no. Could there have been a vertical stretch? Well, this y value of 0 on the original function, if it was stretched vertically, what is 0 times any number? It should still be a 0. So I might think that a vertical stretch has not happened. So what could have happened for this to maybe stretch, shift? Well, we might consider this a vertical shift. We might consider this a horizontal stretch. Horizontal stretch is possible, asymptote's not changing, and a vertical shift is possible if it goes up. Well, do we see any points that that the new graph does go through? It goes through 4, 2 and 1, 1. It was at a 4, 1 and a 1, 0. these do look like they have the very same shape, that everything has shifted up 1. So I might say that this has shifted up 1. So we can take our log base 4 of x and say this has shifted up 1. It does seem like that has occurred. So you can tell sometimes by looking at this location 1, 0, and whether that has actually stretched up, whether that has maybe shifted. If your horizontal or if your vertical asymptote has also shifted, maybe it's a shift, but it looks like this was a vertical shift up. One more at the very, very bottom, and what happens in this one is it looks like that same exact graph has been flipped vertically about the x-axis, and I do see that, you know, if this were to be flipped, maybe this point at 4, 1, when it flips, should go through here, but it doesn't. I see that this y value has of 0 has not changed, so that kind of tells me that this has been vertically stretched. So it hasn't been horizontally stretched out, because that 1 would have stretched out somewhere else. There hasn't been a shift in your asymptote this way, so I'm thinking that it's a vertical flip and then a vertical stretch. So there has to be some vertical flip and a vertical stretch. I'll just put a value in front of that. Well, we might not have to do too much work for this one. If this does flip over, it should be at a y value of 1. If that y value of 1 is stretched out to a y value of -3, but it's stretched stretched from a 1, it'd have to go times 3 to become a 3. So this should say a -3 log base 4 of x. And you can actually plug in, if you really, really wanted to test, you could plug in a x value of 4 and see if it mathematically is sound. If you plug in a 4, a -3 should come out. -3 log base 4 of, plug in a 4, evaluate log base 4 of 4, 4 to the what is 4, 4 to the 1 is 4. And a -3 comes out, which is true. So this does work. So today we looked a little bit at transformations of logarithms as a simple case and using mapping notation to make it more simple. We looked at the characteristics and we looked at getting an equation from a graph. Good luck.